Hello and welcome everybody to the course Crystal Engineering, Chemistry Beyond the Molecule. You remember in one of the first slides I said our task, so scientists in crystal engineering, is to design, construct crystals with desired properties. Yes, this is our task. And I would say in the first step in scientific approach, we try to understand molecular aggregation in solid state, try to understand crystal structures, try to understand intermolecular interactions. And in the second step, I would say in an application-oriented approach, we use our knowledge how crystals are formed, or the molecular aggregation is going on, use this knowledge to design crystal structure with desired properties. Question is, does this works really well? Well, and in this video I will show you some successful crystallization experiments of interesting solids with really nice properties. Well, the title is From Molecule to Material. So from molecule to crystal structure, you can say. Material, yes, this is application wording. Let's go back. Only one step. We have two different categories of intermolecular interactions. I would say we have strong intermolecular interaction, which is important, strong intermolecular interaction to form robust units. Yes, this is the network. Robust units with molecules with specific geometries. This is the network construction. And additionally, we need weak individual interaction. This weak interaction are useful, I would say, to modify our crystal structure, to tune them in such a way, for example, flexibility of this crystal structure. Okay, let's have a look, starting with an explosive material. TNT, everybody knows it. TNT has two polymorphs with a melting point 70 and 80 degrees. And you know TNT is a really explosive material. The question is, can you control with properties? Can you control with explosion properties, with decomposition energy? And the idea is, let's try to synthesize co-crystals of TNT using intermolecular interaction, and with aim that such co-crystals are much more easier to handle. Well, intermolecular interaction in this case means we have a nitro group of TNT and try to build up co-crystals by forming such supramolecular syntones. We have an amino function and a nitro function. Well, and in this contribution of Matzka and Landenberger, Matzka is one of the big guys in crystal engineering, it's very nicely shown that this approach is possible. He published, for example, in this contribution, two different crystal structures. In both crystal structure, TNT co-crystallized with amino derivates. In this case is one, maybe a secondary amino. In this case here, a primary amino. And in the contribution you will see how such co-crystals have an influence on the properties of TNT. So it works successfully. Next examples. You want to deposit aggregates on a surface. Yes? And the question is which procedure, which processes are working in this moment. So we're talking of self-assembly processes on the surface. Can you control the self-assembly processes on the surface? Yes, you can it. It is possible. And you use weak, really weak intermolecular interaction. In this case, we have stable, weak hydrogen interactions on a gold surface. Yes, you construct, you design self-assembled monolayers of molecules on a gold phase by using weak hydrogen bonds. In this case, with weak hydrogen bonds are built by cyano-phenyl compounds. I will show you. Okay, and with cyano-phenyl compounds you have only cyano group, and this is interaction with the phenyl ligand. Well, this is here benzonitrile, for example. There's an interaction with the cyano group and the neighboring sp2ch group here. And in this figure you see two different orientations. One is forming a dimer here, and in the second case you are forming a trimer aggregate. Both show only this weak intermolecular interaction. Here, see it here, and here. Well, this is benzonitrile in exactly in this contribution Nature, top ranking journal. In this contribution they use a little bit bigger molecule, but well, focus here on the substituents of the cyano substituents, and here one cyano substituent, in this case two cyano substituents. Well, and they analyze with their results by high resolution STM images. And they see really nicely in these images the different aggregations of dimers and trimers. With this image, and have a look here. Okay. You see here, this is one molecule, the second, the third. And you see here, this figure is absolutely identical with here, figure 2b. And in this case, you see very nicely, okay, we have two cyano groups, I would say in the para position, something like a para, and you see here dimer and here dimer forming chains. Really nice. Next example, you can use crystal engineering to improve properties of drugs, active pharmaceutical ingredients. This is really a very interesting field for pharmaceutical industry. We are coming back several times on this issue. If you look in the pharmaceutical industry, where always each pharmaceutical industry group has an own group only looking, forming co-crystals and looking for polymorphic behavior of APIs. Okay, only one example here by using hydrogen bond. This is an API ADVO4. ADVO4. Yeah, this is used against hepatitis B. Well, this is the API. The problem is it's decomposed very rapidly. So in the industry, in pharmaceutical industry, or general in health industry, we use not this API, we use a prodrug of this API. A prodrug is, well, a preliminary step of your drug. And prodrug metabolized in the body into the pharmaceutical active drug. Yes, you see in this case with something like Easter. Huh? Okay, so what have they done? They try to improve the dissolution and the stability properties of this product by co-crystallization with saccharin. And it works. What they see is in the co-crystal, they see hydrogen bond, NHO, also phosphorus group, and amide syntons. And now have a look on the properties. This is a figure. Let's go. We have a black here. The black is our product here. The co-crystal is the red one. And a physical mixture, so a mixture of only physical mixture only of a saccharin and the product, not more. No interaction with the physical mixture with the blue one. Well, we see it here the time scale, and here's the dissolution. What we see directly, so we can stay a little bit longer on this picture, or you can stay a little bit longer on this picture, but what we directly see, the first impression is that in a really rapidly, very shortly, in some minutes, you have a high dissolution of the co-crystals. No? Very nicely, independent of a solution. You see it here as an HCl solution and phosphate on water solution and so on, independently of a solution of a mixture, very rapidly dissolution of a co-crystal. Next property, have a look on the stability. So, what we have here, red one, is once again our co-crystal, and the black one is the product. We have two informations here, so depending on the time axis. Huh? One is the content of this product, and the second is the content of impurities, I would say after decomposition. Well, yes. So we see very nicely after a long time, 10, 20, 30, 40 days, 60 days, your product co-crystal is still stable. It works here 100%. And nearly no decomposition. In the case of a product, after some days, only some days, I would say 10 days, mainly 10 days, you see a decomposition process starts, and after 20 days, it's nearly completely decomposed. Very nice, you see it here. No? Nearly no product, and a huge amount of decomposition products. Very nicely, you can use it in this pharmaceutical application way to improve properties. Go on. Next example. Desired properties. Now we are talking about flexibility of crystals. we are talking of plasticity. Is this interesting? Yes, this is interesting. In general, so especially in functional molecular crystals, flexibility is one key function. You can use it to improve the properties of mechanochromic luminescence. You need flexible, weak materials. You can use this to tune the properties of a tabletability of APIs. And it is useful to improve explosive properties. Here's an example. This is the crystal structure of such a flexible organic crystals. Typical crystal structure. And here is really with words were formed by the crystals. Yeah? Were really tunable, very flexible, really weak, waxy crystal. You can use it to form such words here, such figures. Yeah? Well, okay, let's have a look on the crystal structure. What's going on? Well, we have a building block. This is formed from two components, as you see here. This red, I would say the red unit is formed by strong intermolecular interactions. And the tails, the ends of these blocks, you see it here, hydrophobic groups. And with hydrophobic groups in the crystal structure, this is here, the red one here, hydrophobic groups, these are weak interaction. There's a weak interaction between these hydrophobic groups. Yeah? Well, so we have here the columns, here the building blocks, and between the columns are with weak intermolecular interactions, shape syntons. And by pressing exactly in this direction, you can really nice see here, you can bend your crystals in forming such, yes, text units. Very nicely. Going on. Everybody knows MOFs. And you know we will not talk about MOFs. It's an interesting field, but we avoid this interesting field because it's a huge field. Well, but you can form alternates to this covalently bond MOFs by using intermolecular interactions, using hydrogen bonds and halogen bonding. And this organic framework, in contrast to MOFs, are opened and are forming the building two-dimensional channels. And exactly like MOFs, you can use with channels, with holes, with voids to host different gas molecules. How does it work? Well, we are starting from here. Compound 1 has hydroxy group and a nitrogen heterocycle. And this compound, you see it is an iodine substituted pentafluophenol. It's forming such a, unit. And let's have a look on this unit. What do you see? From the viewpoint of crystal engineering, how can you use it? Well, we have two interesting centers. One is with nitrogen here, with a really nice acceptor for hydrogen bond and halogen bonding. And we have this iodine substituent. This is an halogen bonding donor. And now what happens if we crystallize this compound in the presence of H-iodine, iodine acid. this is the result. We are building exactly an open organic framework when, okay, this cross here is exactly this here, or a unit. This cross is unit 3. And now have a look. And the units of 3 are linked by XB, halogen bonding, and linked by hydrogen bonds, forming this very nicely open organic framework. Going on, organic solid chromophores. Organic solid chromophores. The most important thing of organic solid chromophores, also talking about improvement, development, and challenge, and so on, is how can we control the colors of these chromophores, the luminescent colors. And well, in this case, very nicely written here von Jan, is the challenge: how can we obtain light emission of an appropriate wavelength? And his idea was, well, use co-crystals and use halogen bonding. This is the molecule, the fluorescent molecule. Have a look here with P systems of conjugated, yes, P units here, no? Aromatic units. And on both sides we have a cyano group. Well, you remember we talked several times about the ability cyano groups and halogen using halogen bonding, and exactly he synthesized, crystallized materials using this molecule A, this fluorescent molecule, and different coformer. And all of this coformer, you see, except here G and D, have halogen substituents. Have a look on the results. Well, there are some photographs of his co-crystal samples. 1, 2, 3, 4, 5, 6 and A with the powder samples under daylight. A is always the fluorescent molecule, B, C and so on are the coformer. This is over co-crystal 1 from AB, co-crystal 2 from AC, and so on and so on. And all of them are compared with the fluorescent molecule A. Well, I would say there's no really big difference under daylight. But interesting for us is the luminescent properties. And here are the photographs of the luminescence. Wow, and this is a really nice difference to see. No? Blue, I don't know, green, yellow, green, blue, blue, and so on. And with a powder sample under UY, 365 nanometers, if you're really interested, have a look here. And also single crystals. Very nice, and once again with the daylight, and here very nicely under UY conditions. And very nicely, you can use halogen bonding to tune the luminescence emission. You tune the color and have a look in this contributions very nicely. You can tune the lifetime and so on and so on. Nice example for crystal engineering, successful crystal engineering. Good, going on. This were organic solid chromophores. I have shown you an example of successful co-crystal experiments in pharmaceutical interest. You remember this prodrug with saccharin. Now I will show you a successful co-crystallization experiment using halogen bonding. Yes, also possible. Once again, you see here one of the big guys, two of the big guys. Halogen bonding. We are talking of IPBC, 2-iodo-2-propenyl and butyl carbamate. An antimicrobial product, very nicely, and this is the product here. What we see is an amino function, an amide function, I would say, sorry, an amide function here. And you see here iodine is in the structure, iodine substituents. Well, and this prominence is, this drug is very helpful, but has some problems. The problems is it is difficult to obtain in pure form, and it's really hard to handle. Formulation. What you get is a sticky and clumpy powder. And how can you, avoid these problems, or how can you improve the properties? Idea is crystal engineering, improve properties by co-crystallization. We have amide and we have iodine. Okay. The idea is co-crystallization of this drug with halogen bonding acceptors. And typical halogen bonding acceptors are nitrogen heterocycles. For example, bipyridine. See the result here. This is the crystal structure. Here is our API. Here is our coformer. And you see between the APIs we have hydrogen bonds, and additionally between the API and the coformer we have halogen bonds. So it works. Question is, what's going on with the properties? We can compare it with our API, with the co-crystal. Well, and this is talking about, the formulation with clumpy properties. In this case here, you see it's really clumpy here. And in this case, this is the powder of this API co-crystal. Once again, nice examples how you can use halogen bonding in pharmaceutical co-crystals. Well, I hope these are only some examples, and during this lecture series where several times we are going on and looking a little bit more in detail of crystal engineering pharmaceutical industry, or pharmaceutical tasks, because especially in this field, I would say there's a increasing interest in crystal engineering. We can learn really a lot of details, knowledge of crystal engineering, talking about exactly this co-crystallization, polymorphic behavior of APIs.